Hi, we are two students from EECS6895, Columbia University. And today we want to introduce you to our project for this course, a smart traffic system of connected cars. What is smart traffic system? Smart traffic systems are state-of-the-art technology solutions that cities can adopt for fast and cost-effective improvement in the safety and the efficiency of their traffic. In this course, we design a system that can regulate traffic effectively and improve it through connected cars connectivities. And why smart traffic of connected cars? So thanks to the worldwide construction of 5G technology, which brings more connectivity and high bandwidth, new applications in IoT become possible. Based on the research of Business Insider, companies are pouring money into the area of IoT connected cars. As we can see from the chart above, the investment in connected cars has been growing rapidly in the past half decade, and will continue to grow in the future. Thus, with more and more connected cars, which may also bring more congestions on the roads, smarter methods for traffic regulation are becoming necessary. So how's our system works? As the flowchart shown on the left, on the right, users can get access to the smart system through the web page. However, they must log into our system to make use of it. Whenever they want to log out, the system will bring them back to the front page. Once they log in, the navigation endpoint will assign a unique ID for each user and put the information into our database. Thus, after that, user can edit their trip info, such as the starting point and destination. The system will fetch and modify corresponding information. Also, it will update the items in our database for records. Then the system can generate customized maps and return them to users. There are several other useful functions embedded in our system, which will be talked about in more detail later.
So the main data set we use in our project is 2019 New York City taxi trip data. They are public data available from NYC Open Data website. The data set has over 90 million records and 18 columns. Those columns include various information like location, trip distance, fare amount, passenger count, taxi, tax, and so on. Among 18 columns in the dataset, we are particularly interested in taxi pickup and drop-off location and time, since the 3 columns can reflect traffic congestion level. Fare amount is also needed in recommendation for taxi driver part. We extracted and output each row of data by its recorded pickup and drop-off time so that the data could be treated as real time. So the bottom figure shows how the data was pre-processed and columns were kept. Since the data only records the locations as zones, we need to convert the actual map into zone level. We use this dataset to achieve most of the functions in our system. First is congestion level calculation. We calculate average time for each pair of zones and use that time as a standard for comparison to determine congestion level. Based on the data, we can also give recommendations to taxi drivers. Given a time, we can calculate which zone for pickup can have highest fare amount. We then can use this result to tell taxi drivers which zone to go in order to have higher profit. In this section, we will talk about the features that our system has achieved. The first fundamental thing is to build a map and add traffic conditions on it. We decided to use weighted graph to represent our map. where the nodes represent zones and weighted edges represent routes between zones with congestion level. For each pair of zones, we read the data and calculate the average time as the standard for later congestion level determination. After getting the weighted graph, we can then use Dijestra's algorithm to compute the optimal route. For map visualization, we use a library called Folium to display our interactive map. Besides basic route planning, our system can automatically find the gas station when the car's fuel level is low. This flowchart illustrates the logistic. We first searched all the gas stations and marked those zones which have gas stations. An algorithm was developed for this gas station route planning. When the car's fuel level is low, the signal will transmit it to the server. The server first finds the nearest gas station and navigate the car to the corresponding zone. After the car finished refueling, the server then navigates the car to its destination. We also included an aggressive avoidance mechanism for special service vehicles. This is achieved by temporarily modifying the weights of the map graph. In this case, when a special service vehicle is in operation, our system will redirect our other regular cars away from the special service vehicle's route. Our system is also able to give recommendations to taxi drivers to have higher profit. In order to do this, we want to know where to pick up to get paid more. We loaded the whole year's data for each zone as a pickup zone. We sum up all the fares amount. The results then be grouped again by each hour. Finally, for each hour in a day, we can get the top 5 pickup zones that have the most payment. Our system then can mark those zones every hour to guide taxi drivers where to go in order to have more profit.
So here, please allow me to give you a quick demo of our system. So here's a screenshot of our system, and I will bring out our systems to you. So here's the system. Let's say if we got 2 drivers, there's a driver 1, and this driver's 2, and let's start it. So since our map is based on zone level, and the zone level is pretty ambiguous, so we embedded the zone map here as a hyperlink, so users can always refer to this map for their usage. So as we can see right here, different colors means different congestion levels. Let's see, we can test different time. As you can see, the congestion level changed. And now it's our route planning feature. If I want to go from 113 to 161, and as the fuel level is normal, the system will direct the car directly from the starting point to destination. However, if I pick the same route but my fuel level is low, the system will reroute the car to the nearby gas station. And then it's our special mechanism for special service car. Let's say if I want to go from here to there, and I am a special service car, there's a direct route. However, if I want to go from the same starting point to the same destination as a regular car, the system will make sure the regular car stay away from the road of the special service vehicle. And also, once the user log out, is come back to the front page. So let's go back to our presentation. Finally, our conclusion. In this course, we successfully implemented a multi-client smart traffic system of connected cars, and the system can be used by and for them in return. Our system includes basic and advanced route planning, traffic visualization and regulation, and some other add-ons, such as a recommendation system for taxi drivers. Our system also has great business potential. First of all, our system can be integrated into almost any cars by onboard diagnostic device. The OBD can be plugged into vehicles to read the data, such as the fuel level and the tire pressures. So once our system is deployed on cloud, we can also make use of the auto scaling feature of the cloud platform to deal with the scalability issue. Moreover, our system is not limited to cars. It can also be used in other transportation means, such as the city bikes and other locations, such as the shopping malls. Most importantly, our system can be easily upgraded by more data and infrastructures. For example, if we can obtain data from more precise maps or more statistics from cars, such as the average speed, our system could be more accurate and advanced. And I think that's pretty much of our project. Thank you for listening.